All right, well, welcome to week 3. We are now a sixth of the way done with this quarter. We fly, right? Things go by fast. But welcome to another Monday morning. Before we get going on homeworks and all that, just want to let everybody know that the quizzes, I have not finished grading them yet. I'm not going to talk about them actually until later because we still have a couple of students that are wrapping things up with them. So expect on Wednesday that we'll go over the quiz, and you should expect to see your scores up in the next day or two if you haven't already gotten one. So just so you know, that's where we are with that. But let me go ahead and open it up to homework questions. I know that Bailey, you had one. What can we look at today?
So it was in the limits section and it has a fraction minus a fraction and then it's over something else.
Okay.
I didn't know how to factor that out.
Okay, how to deal with the algebra on that? No problem. Do
Yeah.
you remember which problem number it was and which section?
I don't remember the problem number, but I wrote down what the problem was.
Okay. You want to go ahead and just tell me what it is?
Yeah, so it's the limit as t goes to 8
Okay.
of 1 over t minus 1 over 8, and then all of that is over t minus 8.
Okay. Yep.
I think it's like problem 8 of section 2.3.
All right. Well, I'll go ahead and we'll work this one out instead of me going to the homework and trying to search for it because that will take forever. We'll just go ahead and do this because I've got it now. So we'll look at that one. Oh, looks like you weren't the only one. Bailey Leah just put in the chat that she had a similar same question. So let's go ahead and take a look at that. So let me go ahead and share my screen. We'll go to the whiteboard here. And let's see if we can work this thing out. All right, so this is going to be algebra. Again, just like all of these guys, is going to be an algebra trick. But let me just get something off my chest here. This isn't something that I'm proud of. It's not something that I like to share so much, but it's probably important that you know it. I really don't like fractions. I hate to admit that because I know how much everybody else loves them. Of course, I'm being facetious. I'm not being facetious about not liking them. I don't like fractions. I deal with them. I tolerate them, but I don't like them. And if there's any chance for me to get rid of fractions, I do. And this is a great situation of where fractions, at least these fractions that are inside the bigger fraction, can get eliminated quite easily. And all we have to do is multiply top and bottom of this by the common denominator of these, what I call sub-fractions. So if you look at these guys, 1 over t and 1 over 8, their common denominator would be 8t. Right? Easiest way to make a common denominator is just multiply them together. So what I'm going to do is I'm going to multiply the top and the bottom of this fraction by 8t. Okay, so let me just put some parentheses here to show that I'm multiplying top and bottom. Now, this is completely legal. It's completely legal, right? You can build up fractions anytime you want by multiplying top and bottom by the same thing. And I don't really have to worry about this equaling 0 because I'm looking at numbers near 8, right? If I'm going to take a limit as I'm approaching 8, this number is not even close to 0. All right, now, the reason that I did this is that it's going to make it so that things cancel. Right now, when I distribute, right, think about this, I'm going to distribute through. For the first one, the t's are going to cancel, and I'm going to be left with just an 8. So let me just write this. I got the limit as t goes to 8. 8 minus, now this second one, when I distribute through, the 8's cancel, and I'm left with a t. So I've got 8 minus t. On the bottom, I still have 8t times t minus 8. So this is a great trick because now I don't have fractions inside of my fraction, and that makes me a lot happier. I imagine probably does the same for you. All right, so now maybe you see what we can do. Because again, we're trying to get factors that we can cancel, right? And if you look at this on the bottom, I've got 8t and t minus 8. On the top, I've got 8 minus t. Those look almost the same. The only difference is their signs, right? They're plus or minus signs. So what I'm actually going to do is I'm going to factor out a negative from the top. And negative t minus 8. So if you ever have a case where one of the factors looks exactly the same as the other one, just with all the signs are different, pull out a minus, pull out a negative. Because now I can do my slash of those factors. And what I'm left with then is a limit as t goes to 8 of -1, since all that other stuff cancel, I'm just left with the -1 over 8t. So algebraically, what we started with, this horrible thing with the fractions inside of fraction, and the -1 over 8t, those things are exactly the same, except for at t equals 8. But since I'm concerned with near 8, because remember that's what a limit is, near 8, then I can go ahead and do this. And now at this point, I just plug it in, and I end up with -1 over 64. So if you were to plug in numbers near 8, like 7.9, 7.99, 7.999, things like that, you're going to get decimals that are very close to -1/64. They won't be exactly, but they'll be close. They'll be an approximation. All right, so how's that feel, Bailey? Is that better for you?
Yeah, see, I was thinking that might be what I had to do, but then in my brain, I said that's too easy. And so instead, I tried to multiply it by the conjugate for some reason, and that definitely did not work out. So thank you.
Yeah, you're welcome. Conjugates, you pretty much want to reserve those for when we have square roots.
Yeah.
Right? Or if you've got complex numbers, conjugates can be helpful. Obviously, we're not dealing with complex numbers here. So, but yeah, save conjugates for square roots. In general, fractions, the trick is least common denominator.
Yeah.
So, all right, cool. So let me go ahead and stop sharing here. Any other homeworks that people want to see or any other questions? No? Okie dokie. Well, then I'm going to go ahead and switch cameras, get set up over at the whiteboard, and we're going to continue our discussion today. We're going to wrap up our discussion of limits, basically. Where we are right now, we've talked about limits. We've talked about what they are. We've talked about how to find them, and including this algebra stuff. And we also talked about continuity, just the property of functions that involves limits and the function values being the same. But what we need to what I need to show you is how mathematicians deal with close to, right? Like when I talk about the limit, and you hear me say this all the time, you know, where I'll say, well, I don't care about 8. I just care about being near 8 or close to 8. And words like near, close to, those aren't specific enough for mathematicians. Right? In math, we want to be really precise and say exactly what we mean when we say close to, near enough, whatever. So we're going to address that. What I'm going to show you, and I'm just going to be, I'm a straight shooter. I don't bullshit. This is going to confuse a lot of you. And it's probably not good that I start with that, ooh, this is going to confuse it. It has a tendency to confuse people because we start using Greek letters and all kinds of stuff like that. But my goal, and hopefully I can get there with you, is describe it in such a way that it makes sense to you, what the getting near means, so that you have an idea of what it is. I'm not expecting that you get this. It takes people a long time. I know for me, I didn't really get it until I think maybe the 3rd or 4th class that I was presented with the same idea, and then I really understood it. So If at the end of today you're like, oh my God, this was crazy, I don't understand what's going on, yeah, yeah, I'm not surprised. So try not to get into the details and try to see more of the big picture about what we're going to talk about. But anyway, so we're going to get that defined, and then depending on how much time we have, we might start into calculus. We might start answering that question of how do we find instantaneous rates of change. Okay, so give me just 1 second here, and I'll meet you up at the whiteboard. All right. Okay, so as promised, I want to talk a little bit more about what it means when we take a limit of being close. How close is close enough? How do we describe that? Since limits are all about being near a point, we need to sort of define that. So let me give you, first of all, how mathematicians define a limit. Okay, so this is very mathy. I'm going to write it down. You're going to see symbols you may not have ever seen before. Just hold tight. I will definitely answer you the questions. I'll let you know what's going on and I'll explain it, but let me write it out first. Okay. So we say that the limit as x approaches c of f of x equals L, what this means that for every epsilon greater than 0, there is a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon when the absolute value of x minus c is less than delta. So I'm going to give you a second to write this down, and I'll try to explain it a little bit, what's going on here. Okay, so first things first, just some, what are these guys? I'm going to change the angle of this camera just a second. All right, so first of all, this guy looks like a backwards 3 or a curvy E. This is epsilon. It's a Greek letter. It's the 5th Greek letter. It's their equivalent to our E, and in fact, that's where the English E comes from the Greek alphabet. But that guy is epsilon. Okay, why do we use epsilon? No clue. It's what we use. Okay, so epsilon. This one that looks like, I don't know, some sort of a funky music note or something like that. This guy is a delta. Now, you've probably heard of delta, and you might go, well, that's not the delta I know. You may also know that there's a delta that looks like a triangle. Well, that's the capital delta. This is the lowercase delta. So just like in the English language, we have different symbols for capital letters versus lowercase letters. Same thing in Greek. Okay, so this is the lowercase delta. This is the lowercase epsilon. A capital epsilon looks like a capital E that we write. Okay, so these are just Greek letters. Don't let that throw you. Okay, don't let that throw you. These are just letters. Just like any other letter, they're unknowns. They're variable. They can change. Okay, and in fact, it's necessary that we allow them to change when we talk about limits. But that's epsilon, and this is delta. Delta is the 4th Greek letter, and it's equivalent to our D. Anyway, so it says here, for every epsilon greater than 0, there is a delta greater than 0. All right, well, just catch that epsilon and delta are both positive numbers. it turns out they need to be positive because they're going to be distances. We're going to look at this graphically. We're going to think about this graphically, and those are going to be distances. Okay. All right. And then we get to this stuff. And this is usually where everybody gives up. They just go, yeah, never mind. But let me just kind of explain what's going on. So this first one, we've got an absolute value of f of x minus L. Okay, so f of x is just our function value. And L is the limit. It's the number that we're going towards. Okay, so we're just looking at the difference between our function and the limit. How different are those? This other absolute value, x, of course, is what we're plugging in. And c is where we're approaching. So x minus c, again, is a difference. It's what's the difference between what we're plugging in and c. All right, but then we've got this little absolute value, the fact that the first one is less than epsilon, the second one's less than delta. I'll explain that here in a second. Okay, so we got that. So now let me actually draw you a picture so that you can see what this means. All right, give me 1 second here, folks. Got a slight technical issue. Okay, so let me draw a picture. We're just going to start with regular old axes like we're used to. And then I'm going to put just some function on here. It's an unknown function. It's just a random function. It doesn't really matter. But here's our f of x. Okay, so this is f of x. And let's pick an L and a c. Okay, so we're going to have some c value. And this is the value that we're approaching. And then we're looking for the limit. So if we were to kind of run up here, just from the graph, it looks like this would be our L. So we'll go ahead and mark those guys L and C. And so here's our little picture. Okay, so now let me explain what epsilon and delta are. So epsilon, this is going to be a number that's just given to us. All right, and epsilon is telling us how close our function needs to be to L. Our function values need to be to L. So here's how I want you to think about epsilon. Epsilon is a distance that we go up and down from our L. So you can think of it as like a tolerance. I like to think of it as a epsilon is telling us how close we need to be to our limit value. So think about that example we just did, the homework question that Bailey asked about, where we found the limit was minus 1/64, right? So minus 1/64 is just a number. Epsilon, given an epsilon, we're saying you need to be that close to minus 1/64. So maybe epsilon is 0.1. What we're saying here is that we need to be within 0.1 of 1/64. Or maybe epsilon is 0.003. Okay, well then we need to be within 0.003 of it. So basically what epsilon is telling you is how close do you need to be? How close does your approximation need to be to the actual value? Okay, so that's epsilon. Delta is a distance away from C. And so delta is going to be over here. But basically what delta is saying is that if you are within that distance of C, all of your function values are within the tolerance or within the approximations limit that we want, right? How close we can actually be to that. So on the graph of this, think about going up epsilon and down epsilon. That kind of forms a horizontal strip, okay? So that's my plus epsilon, here's my minus epsilon. And what I'm looking for is where on this function am I going to be entirely within this horizontal strip? And you can see that that actually happens here. So let me just kind of fill it in green so it's a little bit different color. But if you look at this bit, all of that is within the tolerance that were specified. Okay, so if I actually had those numbers, what we would see is that all of these values are within that strip. So the delta is just how far can I go from C so that I'm somewhere in this strip. Well, let me run these guys down. So basically, I just have to pick a delta, which is a step away from C, such that if I were to go that far either direction, all of the function values are still in this strip. Now, there are a lot of choices for delta. So I'm just going to show you one of them. And so I'm going to say, let's make it so that this is my delta. So I'm going to go the same distance on either side. But notice that if I just restrict myself between the values plus in the C plus or minus delta, everything in that function, in that interval, lies within my tolerance. Now, I could make delta bigger, right? Because there's still more I could include. I can make delta smaller, because if I shrink this down, it's still within that strip. But this is what our goal is going to be. Okay, so epsilon is how far are we from the limit? That sets our how close we got to be. And then we go and we find a delta. So think of this as a game. Think of this as a challenge. All right, someone's going to give you an epsilon. Or you might say, okay, hey, so Bruce, give me an epsilon. I say, all right, I want you to be within 0.05. Your goal is to find an interval around C such that if I were to plug any number from that interval in, what comes out of the function is within the 0.05 that I gave you. All right, so sometimes I'll call this the epsilon delta game. Given an epsilon, find a delta. Okay, now, if you come back and you look at this definition, there's a very important word, and it's right here. It says for every epsilon, there is a delta. All right, so that means no matter what epsilon you throw at me, no matter how close you tell me to get to the limit value, I can always find an interval around C. I can always find it. So that everything in that interval, when I plug it into the function, gets me within the tolerance that you just told me. Okay, even if epsilon is like 0.0 with a million zeros, 1, I can still shrink that delta, get that delta small enough that everything in that interval, when I plug it into the function, is still within that tolerance. Okay, so if you can do that, if no matter what number you give me, whatever epsilon you give me, if I can still find that guy, that little interval, then my limit exists. If there's ever a point where I can't make an interval small enough to actually get that, well, that's when the limit doesn't exist, and we've kind of seen that. So let me actually show you that first. Let me show you some issues with limits not existing that we already know about, and then why this definition doesn't hold, okay? So make sure you got this definition written down because we're going to use it. So here's an example of a place where a limit doesn't exist. And you've seen a few of them, so let me just show you a couple of them and why this thing fails to hold. Let's start with the jumps. Remember those guys? The ones where, as we were approaching from each side, we got a different value. So something like this. Okay, so you already know the limit doesn't exist here. We've seen that. Now I want to show you why this fails in terms of the epsilon delta thing. So imagine that we made a guess for our limit, and you might go, well, let's just take this point and say that this is L. So maybe we think this is the limit. Okay, so then this is C. So what we have to do is that given an epsilon, we have to find a interval around C such that all the function values are within that distance away from L. So let me give you an epsilon, right? Because remember, it's for every epsilon. So here is n epsilon, right? Here is a choice. So I'm going to say, let's go up this far, which means we're also going to go down this far. So I'm going to make a tiny little horizontal strip. The actual numbers would be L plus epsilon and L minus epsilon. So if you had those numbers, you would just add or subtract. But that's my little strip. Okay, so now think about trying to form an interval around C. So,
Excuse me, Bruce.
we've got this piece right here, and we've got that piece right there. So are all of those blue pieces within the green strip? Think about that function. Is all of that within my little epsilon strip?
No.
And you can see that it clearly isn't, right? Because think about this piece up here. That's not within that green strip. And it's impossible, it's absolutely impossible to shrink this interval enough to make it fit inside that green strip. Because there's always going to be a little bit that's outside of it, right? If I make this delta smaller, well, we'll take care of this piece, let's say, that's outside, so we got to shrink it in, but there's always going to be another chunk that's not entirely in that strip. All right, so this is the kind of thing that's happening graphically when limits don't exist, and it all comes back to this epsilon delta. So
Is that because,
let's, yeah, I'm sorry, go ahead.
is that because you have to have the same direction out on either side? Like you couldn't just have one all the way up to the point?
Correct. Yeah, we need to go delta in both directions, unless we're doing a one-sided limit. If we do a one-sided limit, then we only care about the one side, and now we know that we can do it, right? Now we know we could, if we could ignore that piece, we can shrink this small enough so that it fits inside that horizontal strip.
Okay.
So yes, it does have to be both left and right, unless we're doing a one-sided limit. Okay, so we see the same thing with like infinity. Like think if there was one that was infinite, right? So let me just put here an infinite limit. If I drew a graph of an infinite limit kind of issue, let's just take, say, something that looks like this. And so maybe we're approaching this guy C. If we thought there was a limit somewhere, say this guy is L, we build our horizontal strip of plus epsilon and minus epsilon. And the problem is that no matter how close I get to C, there's always going to be part of this function that's outside of that strip. Right? There's always going to be this piece that's up above, no matter how much I shrink this down. So all of the issues you've ever seen with limits, they fall from this definition. Like you'll see how they don't follow this definition. So basically, think again what we're trying to do. Epsilon is create the strip. Tell me how close to be. Tell me how much tolerance I'm allowed. Delta, okay, I shrink my interval so that all of the function values are within that tolerance. So let's do a specific one. Let's plug in some numbers. Let's have an L, an epsilon, a C, right? And then we'll find a delta, because I think just drawing pictures and all that, it's still probably just still for some of you. Let's plug in some numbers. Let's actually try this. And we'll go to a nice function. Let's go to good old x squared. We like f of x equals x squared. It's pretty useful. Let's actually plug in, choose a C, look at the limit, and then we'll do the whole epsilon delta business. All right, so let's look at this guy. F of x equals x squared. And we're going to look at the limit as x approaches 2 of x squared. Okay, so what is that limit? What's the limit as we approach 2 of x squared?
4.
All right, good. Just 4, right? We just plug it in when all else fails, right? Just plug it in, 2 squared is 4. So it looks like this should be equal to 4. Okay, so in terms of all the different letters and everything, that means that L is 4, C is 2. Now, what I'm going to do is I'm going to give you an epsilon. All right, so let's look at given epsilon equals 0.1. Let's find a delta. So again, with this limit definition, it says that given any epsilon, we can find a delta. Well, here is n epsilon. Let's find it. Okay, so basically, what we know now is that we want our function value to be within 4.1 and 3.9. So before I move on, are you all good with how I have 3.9 and 4.1? I'm going to take no comment as, yeah, we're okay with that. Because again, all I'm doing is I'm going plus or minus that epsilon. I need to be that close. I'm going to be within plus or minus 0.1. So I just went up 1.1 and down 0.1. Okay, so let's figure out what x values actually make those happen. Right? So let's look at when f of x equals 4.1. And let's look at when x squared is equal to 3.9. So again, I'm just looking at where does my function actually equal those two values. All right. So where does it equal 4.1? How am I going to answer that?
You square it, like square root.
Yeah, I'm just going to take the square root and see what I get. All right, so if anybody's got their calculator handy, go ahead and do that. What do you get with the square root of 4.1?
2.02484567
All right, awesome. So let me go ahead and write that down. So 2.02484567 I figured that's probably close enough or far enough. So 2.02, did you say it was 484?
4845673.
Okay, well, we'll go with that. So it's 2.02, 484, 5673, something more, blah, blah, blah. Okay, but this is the x value that's going to get us to 4.1. And you notice that it is kind of near 2, but we can go a little bit bigger than 2, obviously. Okay, so do the same thing with 3.9. So we'll take 3.9, take its square root.
1.9748.
Okay, so this is around 1.9748. And I think it's like 417 something. Okay, so those are x values that will bring us to 3.9 and 4.1. So on a graph, here's what's going on. We've got our x squared. We're somewhere near 2. Okay, so like let's just say that this is 2. So here's our point that's 4. And these two numbers, the 2.02484 and the 1.9748, those are x values. I'm going to exaggerate this a little bit. Those are the x values, such that all of those y's, so if we were to look at this strip right here, all of those things are within plus or minus 1. Okay, so again, clearly not to scale. All right, so we were given an epsilon. Now we need to pick a delta. So basically the question is, how far can I go from delta, or sorry, from 2, such that I'm still in this interval? Well, like I told you before, there are lots of choices we could use for delta. Here's the delta I'm going to pick. I'm going to pick delta equals 0.02. So think about this. If I went bigger than 2 by this much, I would get 2.02, which still isn't as far away as I could potentially get. Right? I could go a little bit further and still be within this value, but 0.02 definitely makes it work. If I subtract 0.02, I get 1.98, which is still within this interval. Right? Now, could I pick any other delta? Sure. I could pick 0.024. That would work. I could pick 0.00001. And it doesn't really matter. I just have to be able to find a delta. So given an epsilon of 0.1, I pick a delta of 0.02, and therefore everything in this interval is going to be within the horizontal strip. So for a limit to exist, you have to be able to do this for any epsilon. And basically what happens is as epsilon gets smaller, delta is forced to get smaller as well. Big epsilon, you can have big delta. Small epsilon, you need a small delta. Okay, so given a function and an epsilon, this is how you can find your delta. But remember, it's one of the deltas. In fact, I could pick any delta smaller than this and it'd be fine. If I were to ask you to give me a delta on any one specific problem, you all could give me a different delta and still be correct. Okay, because it's just we have to find an interval. It doesn't say find the biggest interval. It just says find an interval. Okay, so here's what's going on. It's just it's a real technical thing, but it's how do we get close enough? Now, mathematicians, of course, we don't want to have to do every time, well, solve the function equal to for this new epsilon, calculated delta, right? We like to do it one time. We're super lazy, right? We try to do everything once and only once. And we're going to do that. I'm going to show you how, given an epsilon, you can actually calculate what the delta is without plugging in the specific epsilon. Okay, but to do that, I want to talk a little bit more about the absolute value stuff that we saw in those equations. So in the definition, so if you go back and you look, you saw there were two absolute values. There was the one that said absolute value of f of x minus L is less than epsilon. And the other one that said the absolute value of x minus c is less than delta. Now, if you look at what I wrote at the very beginning with this one, where I had the 3.9 and the 4.1, I want you to see what happened there. F of x minus L, remember we had an L value? For that one, it was 4. And I also gave you an epsilon of 0.1. Well, I don't know if you remember your absolute value inequality stuff, but you can actually turn this into a compound inequality. If your absolute value is less than a number, it's the same as the thing inside being less than that number and greater than the negative. If you don't remember that, or kind of confused, or don't not kind of seeing that, I'm going to have you go back and reference a pre-calc book or an algebra book, because it's one of the things that we do somewhere back there. But to solve this, you would just add 4 to each piece, and you notice that that gives me 4.1, 3.9, and my f of x. So really, when I set this thing up, and I think most of you seemed pretty okay with the idea of, well, yeah, we just need to be within that. It's coming from this inequality. All right, so then if you think about this delta thing, you could do the same thing with that inequality. And so we'd have, say, x minus, in our case, 2, less than delta. Well, I chose 0.02 as my delta. If I were to rewrite that as a compound inequality, is it just telling me what the x values are in the interval where I'm guaranteed to be within this little strip. Okay, so we actually were kind of doing that, using those inequalities. It probably didn't feel like it, but we were. They were actually part of it. Okay, so if we're going to try to prove this, we're going to try to prove something, a limit existing, using epsilon and delta. Basically, the idea is we're going to start with this first inequality. Okay, we're going to start here. And then we're going to use algebra to get the other one. So we're going to do some sort of algebra to actually get the other inequality. All right, we'll come back and we'll revisit this x squared. But let's actually start with an easier one. At least it's going to be easier algebraically, especially with the epsilon delta. Okay, so let's do this. Let's take the limit as x goes to 4 of 3x minus 1. So what we're going to do is we're going to find the limit, and then we're going to prove that that limit exists. Okay, so first things first, what's that equal? What's the limit as x goes to 4 of 3x minus 1? All right, good, Mariel, thank you. It's 11, right? Let's plug it in. 3 times 4 is 12. 12 minus 1 is 11. Okay, so in the context of everything, let's just sort of, let's write what everything is. So f of x, this is 3x minus 1. L is 11. And C is 4. I'm not specifying an epsilon. Epsilon is going to be epsilon, and delta is going to be delta. But let's start with this first inequality. So we're going to have the absolute value of 3x minus 1 minus 11 is less than epsilon. And we want to play with this thing. Okay, so we want to fiddle around with this until we get absolute value of x minus 4 is less than delta. All right, so that's what we need it to look like. We need it to look like the absolute value of x minus 4 is less than delta. So let me actually write that up here just as a reminder of where we're going. Because I want to do the steps down below. All right, so let's start filling with this and see if we can get an x minus 4 inside the absolute value. So obviously, first thing to do would be to combine like terms. So if I do the subtraction of the 11, I get 3x minus 12 is less than epsilon. All right, a next step here would be factoring out the 3. Because 3x minus 12, I can factor out a 3. And notice we're getting close. We almost have the x minus 4 all by itself. So the last step is going to be, let's divide it by 3.
Sorry, what are we trying to get here? Are we trying to solve for
I want the
epsilon?
absolute value of x minus 4. Remember, that's our goal. We want, this is what we're trying to get. Maybe I should write that up here. This is our goal. It's to get absolute value of x minus 4.
Why is that the goal? I'm confused about what our main focus is here.
Hold on one second, because I think it'll be clear as soon as I do this next step. So just I think we're really close early. After this next step, if you're still not seeing it, let me try to explain it a little bit more.
Okay.
So all I got to do is divide by 3. And so I've got absolute value of x minus 4 is less than epsilon divided by 3. Okay, so now let's just think about what we did with that numerical example of x squared, right? I gave you an epsilon. I said, hey, be within 0.1. We did a little bit of math, and we found a delta, right? So the whole goal of all of this is, given an epsilon, find a delta. Well, now what we've got, remember that when I said the goal was to have this absolute value of x minus 4 is less than delta? Since I've got the absolute value of x minus 4, that tells me that this guy right here, epsilon divided by 3, that's my delta. Because look at the structure of these. Absolute value of x minus 4 is less than delta. So all of this stuff is my delta. So here's what just happened. I now have a way to find a delta no matter what you tell me epsilon is. Okay, so if I say, hey, give me an epsilon, no matter what you tell me, I'm going to say, all right, pick delta to be 1/3 of it. If it's 1/3 of that epsilon, I know that my interval is going to be small enough. So the whole goal here, really what we just did, was we found it, we crafted delta, right? So now we can say, given epsilon, pick delta equal epsilon divided by 3. And so the reason that we needed to have x minus 4 all by itself is because then whatever's on the other side is my delta. So did that help Aaliyah a little bit in terms of why we're going there?
I think so. Is this kind of like a pre-step that you would do before you were given an epsilon in order to figure out the delta from it?
Yeah, actually. So now, like, let's say someone says, well, let's pick epsilon equals 0.04. Okay, well, I'll take that 0.04, I'll divide it by 3. And as long as delta is that or smaller, we're good to go. But really, we did this so that we don't have to do it every time, right? Because now if there's a rule, since I've got a rule here, I know this is going to work for any epsilon. And that's enough to show, that the limit exists. But go ahead.
I guess my main question is like, how would this question be laid out? Like what was our initial ask?
Okay. So it depends. Okay, it honestly, it depends, especially on the homeworks, because on the homeworks, it will ask you to do a whole bunch of different things. But basically, if it said, prove a limit, right? So prove that the limit as x goes to 4 of 3x minus 1 is 11. Okay, so if we want to prove that that limit is 11, we have to be able to find some way of specifying delta for any epsilon. And by me being able to write this statement right here, given epsilon, pick delta equal epsilon over 3, I now have a delta no matter what. No matter what, I know I'm just going to divide your epsilon by 3. This is enough to prove that the limit exists. Now, we would have to write something up. Like a mathematician wouldn't just do this. They would write something like, okay, given an epsilon, let delta equal epsilon over 3. Then, if x minus c is less than delta, we have x minus 4 is less than epsilon over 3, which if you do some algebra, show the steps, kind of go backwards here, gives us this, which shows that f of x minus L is less than epsilon. So if you're actually going to prove it. And we're not going to do that. And I'm not going to expect you to be able to do that. That's for a later class if you go further. Again, like I said at the beginning, I want you just to get the general understanding of what's going on. But the goal for a mathematician always is, I want to be able to answer this question no matter what you give me. And the easiest way to do it is if I do all the work one time, right? Once I do this algebra once, I never have to do it again. And now it really is as easy as, all right, every one of you start giving me an epsilon, I can just, boom, tell you what delta is. I don't have to go through the intermediate steps and calculate and, like that one with the x squared where I take the square root of 4.1 and I take the square root of 3.9 and I figure out, how far away are those from, right? I don't have to do that anymore. Now, I divide by 3. So basically, this algebra is what tells us how far we can go horizontally in our interval. As long as delta is epsilon over 3 or smaller, we're good to go. All right, I don't know if that actually helped, but that's kind of the idea here. All right, let me try one more here. Let's do another one. And let's try making it the absolute value of x. And we'll look at the limit as x goes to 0 of the absolute value of x. All right, so what do you guys think that limit is?
0.
All right, probably 0. Do the same thing, right? Plug it in, see what we get. It looks like it might be 0. Okay, so in this case, f of x is absolute value of x, L is 0, and c is also 0. Okay, so let me start with what our goal is. The goal is going to be the absolute value of x minus 0 is less than delta. I was going to this last inequality. And I'm putting in the c, which is 0. Well, obviously subtracting 0 just means we've got absolute value of x. Okay, so this is what we want to end up with. We want just the absolute value of x. Because if we have just the absolute value of x, then whatever's on the other side is going to be our delta. All right, so let's go to what we start with. So we're going to start with the absolute value of x minus 0 is less than epsilon. So this was my f of x minus my L. So f of x minus my L is less than epsilon. So let's play with this one just a little bit. Obviously, subtracting 0 is just going to give me the absolute value of x. And if we take the absolute value of the absolute value, the second absolute value is redundant, right? Think about what absolute values do. They return a positive number. So if I take an absolute value of a positive number, it's still positive. So this is actually the same as the absolute value of x is less than epsilon. Okay, but now notice that this form right here matches the form that we want. And so what I need is everything on this side of the inequality to be delta. So in this case, we're going to let delta equal epsilon. So this one's actually really easy. So if I said, okay, you need to be within 0.1 of this limit, I would say, okay, well then don't go further away than 0.1 from 0. Or you say, I need you to be within 0.005. Okay, don't go further away than 0.005. Whatever you give me as an epsilon is what I'm going to return as a delta. But since this first inequality was able to end up looking exactly like the second one with this epsilon, that epsilon is our delta. So whatever's left over here after you do the algebra, that's what we pick to be our delta. So this one was actually really fast and easy because there wasn't much algebra to do. Subtracting 0 is simple. Absolute value of absolute value, yeah, that's nothing. Okay. Sometimes the algebra is rough, like we'll see in this next example. But basically, again, our goal is to get whatever that x minus c is. We want that in the absolute value so that anything on the other side is actually our delta. All right, questions on this one? And I imagine we're still in the, I have no idea what we're doing here. It'll come, read about it, look at it a little bit more. But basically, we're just generically saying, here's how wide we can make our strip, our interval around C, so that all our function values are within the tolerance that are specified. Right, we're just doing it one time. Do algebra once, because then it's easy. Okay, so the last one we're going to do, let's go back and look at the one that we started with, which was x squared, and the limit as it went to 2. Right, so we had the limit as x goes to 2 of x squared, which we saw was equal to 4. We're quite confident in that. So here are all our different things. So f of x is x squared. L is 4, C is 2. So in terms of our goal, we want the absolute value of x minus 2. So that's what we want to end up with inside of our absolute value, just x minus 2. What we're going to start with is the absolute value of x squared minus 4 is less than epsilon. So that was our f of x minus L less than epsilon. All right, so what algebra do you want to do here? What do you think? What can we try?
Add 4 to the other side.
Okay, we could definitely add 4 to the other side.
Can we just square it?
Ish. Okay, squaring it, I don't think is what you mean. Maybe
Square rooting, sorry.
taking a square root. The problem with square root is the fact that we're subtracting. And when you take a square root, if you got addition or subtraction, you just can't take a square root of both pieces. So what we're actually going to want to do is what Leah just typed in the chat. I don't know if people saw it, but we want to factor. X squared minus 4 is a difference of squares. So we can actually write that as x plus 2 times x minus 2 and since I've got multiplication, I can actually split that. I mean, I can pull that apart. But I'm going to have here the absolute value of x plus 2 times the absolute value of x minus 2 is less than epsilon. These absolute values right here are necessary. They are absolutely necessary. Sorry, that was bad damage. All right, these absolute values are needed because x plus 2 could be negative. There is the possibility that x plus 2 is negative, and we need this entire result to be positive since they were all inside absolute values. So if you're going to split absolute values apart with multiplication or division like this, make sure you just keep everything in absolute values. Now, this first one, it's not really going to be negative. At least not where we're interested in, right? Think about this. Remember what we're doing is we're forming an interval around 2. And if we're near 2, this is not going to be 0 or negative, right? I mean, we got to be pretty far away for this to turn negative. You got to be down past like -2, which is pretty far away. And with limits, we're trying to be close, right? But in general, that's a good idea. Just keep the absolute value. All right, so now if we were to divide by that, we now have our absolute value of x minus 2 like we wanted, and all this other stuff. Okay, but we're not quite done, unfortunately. Because here's a problem. If I were to say, okay, let's pick delta to equal epsilon over x plus 2, well, what x value? Well, it kind of depends where we are, and this is going to be changing depending on where we are. So I really don't like this as it is right now. So we're going to play just a little bit of a trick. It's a minor little trick, but think about this. If we're near 2, because that's kind of what we're looking at, right? So I'm going to put here, quote unquote, near 2. What if I were to say, okay, my x's are going to be between 3 and 4. Or, sorry, not 3 and 4, 1 and 3. Does that seem reasonable? That I think anybody's definition of close to 2 or near 2 means that those values are going to be somewhere between 1 and 3. Yeah? I mean, if you don't like that, we can make it closer. We can make it 1.5, 2.5, 1.9, 2.1, 2.1, whatever you want. But I think that that's at least sufficient for near 2. So let's just say that we know for sure x is going to be between 1 and 3. So then x plus 2 is going to be something between 3 and 5. Again, if that's not near enough for you, go ahead and get near whatever you want. Shrink that initial thing. But I'm good with x plus 2 is going to be between 3 and 5. Okay, so then what that tells me is that epsilon over x plus 2, and the reason I'm going to epsilon over x plus 2 is because that's what we wanted our delta to be. I know that that's going to be something between epsilon over 3 and epsilon over 5. So I'm just taking epsilon and dividing by those things. But I did change the direction of the inequality. And that was intentional. Because when you divide by numbers, the inequality swaps. If you divide by something big, you get something small. Okay, so dividing by the bigger number actually results in the smaller value. All right, now notice what I did was that while I don't know exactly what epsilon over x plus 2 is, I do have, well, an interval in which I know it lies. I know it's somewhere between those two numbers. Okay, so here's what I'm going to do. I'm going to pick delta to be the smaller one. And the reason I'm going with smaller is that we can always shrink delta. Remember when we were first talking about it in that very first one? I think it was actually this one when we were given an epsilon and we chose delta equals 0.02. And I said, well, it could be smaller if you want. You can go with any kind of smaller number you want. So in general, smaller is better. So here's what I'm going to do. I'm going to pick the smaller of these two, epsilon over 3 or epsilon over 5. And the smaller one is the epsilon over 5. So that's what I'm going to let my delta to be. So as long as being near means I'm in here, I'm within 1 over 3, then this is a perfectly fine delta for me to choose. So here's how I would write this out mathematically, though. I would say pick delta, let delta equal, and I'll explain this in a second. So I'm going to write min, put parentheses here, 1 comma epsilon over 5. And for some of you, you might be going, man, I was just getting a handle on this, and then he threw in all this new symbols and stuff. Let me just explain this real quick. So the epsilon over 5 just came from us running the math. Okay, but now what this is saying, min, this is the mathematical way of saying take the smallest thing from this set. The little curly braces, that's set notation. So basically pick the smallest thing from in here. Either 1 or epsilon over 5. So hopefully you're kind of okay with where the epsilon over 5 came from. Yeah. But where the 1 came from was from me choosing this interval right here. Because notice that this is 2 plus or minus 1. That's the 1. So when I first said, hey, that feels close enough, and I said, yeah, if you want, make it 2.1 and 1.9. So if we had done that, if we had said x is between 1.9 and 2.1 and then done everything, then we would have said let this be the minimum of 0.1, comma, whatever it would have come up with. All right. But basically, I now have a way of doing this. You give me an epsilon, I will divide it by 5, and that's going to be my delta, unless that's bigger than 1. And then I'll just say, okay, well then let delta equal 1. So the math behind this stuff can get really gnarly really fast. This was just x squared. Imagine you were trying to do this with a trig function, a log function, fraction, right? I mean, it can get pretty brutal pretty fast. That's not what we're concerned about, all right? You want to deal with that stuff. You'll deal with that stuff later if you're a math major. People who are not math majors don't do this, just FYI. Like this is all you're going to see of this. It'll come back a couple of times through calc. We'll do just sort of a, oh, hey, remember when we did this before? You can do it again with blah, 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 right? But you're never going to really prove things with it because that's for math majors. That's for people like me, right? I had an entire class of we proved calculus. We proved everything in calculus using epsilons and deltas. All right, well, it's a math major class. That's what math majors do. So if you're still kind of like, man, I don't really get it, and all of this algebra stuff, yeah, that's okay. But just think about what we're talking about. This is how close is close. And for a limit to exist, no matter how close you tell me to get, I can get closer. That's really the idea behind the limit. If you can't do that, the limit doesn't exist.
I have a quick question.
Sure.
I understand what you did with that whole second step there, starting with near x equals 2, but why did you want to do that? Was it because you didn't want x on the epsilon side at the end of that first step?
Yes. Yeah, this right here is no good. Having a delta with x in it doesn't work because x changes in like in a little interval. That x is going to take on a different value, and so the question is, well, which one is it? I can't have that. I have to have a specific number. So that's why I did this. I went to see what is that, what are those x values? How do those relate to actual numbers? So that I would have a specific value in here. I'd have 5 in this case. But yeah, that's exactly why. The two variables errors is not as big of a problem as you might think, because later, like when we get to third quarter calculus, we'll start doing things with multiple variables, and it's actually okay. It's more the fact that this number is changing, and with delta has to be there is no option, right? It's like, no, this is the delta. And the problem is if I say delta is epsilon over x plus 2, that number varies. Epsilon over 5 doesn't vary. That's the number. So that's really the issue. So I think, was that you? That was you, Aaliyah, right, that asked that question?
Yeah, and sorry, just one quick follow-up.
Sure, no, please, go ahead.
X varies because we're not actually plugging in the limit. We're talking about getting close to the limit. Is that why it varies?
Yeah, the fact that we're making an interval. Remember what delta is doing is specifying how far away we can get. So in this case, how far we can get away from 2. And so we're making there's a whole set of x's there, because it goes from 2 to a number a little bit bigger and a number a little bit smaller. We have a whole bunch of different x values. And every single one of those x values, if you were to plug it into this, would give you a different number. And then I don't know if you noticed the issue with this, right? If I start adjusting my delta, I start adjusting my possible x's. Well, changing my x's now changes my delta, which changes my x's, which changes my delta, which changes my x's, which changes my delta. And we get in this horrible loop of there isn't now a way of doing it. So by just sort of saying, okay, no, let's just first say x's are trapped. X's are for sure in here, like I did here with the 1 to 3. Then I don't have to worry about those x's are now changing my delta, which is changing my x's, which is changing my delta, right? And so that's really the issue here, is that x, there are lots of choices for x because we've got an interval around our number that we're looking at. Does that help? Kind of, maybe, hopefully. Well, I'll tell you what. So if you guys are still, like, after you get in there and play a little bit with them, with the homeworks and all that, I'm sure questions will come up and we can chat about them again. Remember, at the beginning of class, anytime you guys want to ask about things, I full on anticipate we're going to talk about this on Wednesday, right? Wednesday morning. And so we'll revisit it for sure. But I want you to try it out and try, you know, specifically start with the ones where you have are given a value of epsilon, you know, where they say get within 0.5, get within 0.02, and play around with it just to get the feel of what's going on. But basically, it's just that no matter what kind of horizontal strip you give me, right, whatever one of those strips, I can actually shrink my interval so that my function in that interval always lies in that tolerance. You tell me how close to get, I can get that close. All right, so as I promised, this stuff is a little bit weird, but it's how mathematicians define limits. This is how we make it so that there is no question on what is near, what is close. Right? All right, well, now that that's done, let's actually start looking at calculus. Let's answer that question of how do we find instantaneous rate of change. So just so you guys know, because you're probably wanting to play along with your notes and write what's going on, we are now moving into chapter 3. Okay, this was the last section of chapter 2, if I recall correctly. And so we're going to be moving into chapter 3, and chapter 3 is all about the derivative, which is the tool we use to find instantaneous rate of change. So let me just, with the time we've got left today, remind you about the idea of instantaneous rate of change and then what this has to do with, say, limits. Like, why do we even care about this? All right, so remember the whole speed thing? We were talking about like how fast the pen is moving when I toss it in the air and all that. What we were looking at was, given some sort of a function, we wanted to know, say, the instantaneous rate of change at this value that I'm going to call C. And to get the instantaneous rate of change, that meant we wanted to find the slope of the tangent line. But the problem with finding the slope of a tangent line is that for the tangent line, we knew only one point. And you can never find slope if you only know one point. So the trick to this, the workaround, was to find a second point somewhere a little bit further out here. So I'm going to call this C plus, say, H. And find its function value. And then we could actually connect those two dots with a line. And create a secant line. Now what we saw here was that the slope of the secant line, this was the average rate of change. So this is nothing new. We already talked about this, and in homework set, whatever that was, 2.1, you actually did this, right? You actually calculated some. But now let's talk about how we take these secant lines and we make it so we get a tangent line. So what did we do to make it a better guess? You guys remember what we can do with these secant lines to make them a better guess?
Bring the 2 points closer together.
Yeah, if we bring those 2 points closer together, like if we're talking about the pen up in the air, we're shrinking our time interval. And we know if we got a smaller time interval, then the speeds are going to be more consistent throughout that time interval, more likely to be roughly the same. And so the idea was, let's just shrink that interval. So we want to bring this point, we want to bring this second point in towards the first one, which means I want to bring this c plus h in. All right, now, here's where the whole limit idea comes in. Let's just think about this slope for a second. So I'm going to write here m with a sec below it. So that's slope secant. We're going to find it by doing the change in y divided by the change in x. So what I wrote there, the f of c plus h and the minus f of c. So those are the y values from plugging in these two numbers. And then those two numbers are the x values, so that's why I put them on the bottom. And I'm just going to do one thing. I'm going to rewrite the bottom because the c's cancel. Right, c plus h minus c leaves me just h. So this is how you could actually calculate the slope of the secant line, or your average rate of change. All right, now if I want to change this then to slope of the tangent line, so m tan, I need these 2 points to get so close together that they look like they're just 1 point, which means I need this step to shrink. So what I'm going to do is I'm going to take the limit as h goes to 0 of this value. And hopefully you can see that through the glare. It's the exact same fraction that I had up above. I'm just now taking a limit as h goes to 0. So by introducing this idea of limits, I now can actually find instantaneous rates of change. And this was the big leap in calculus, was being able to see this limiting idea. Okay, so this is one way that we're going to do this. But there's another way that you can view this that looks a little bit different. I'm going to use the same picture, but I'm going to label things a little bit differently. Instead of c plus h, I'm going to call this guy x. So think about what this is going to do to our tangent line. I'm going to leave a spot for a limit. We'll write what goes in there in a second. But if we think about this fraction then, the y's are going to be f of x and f of c. And the x values, of course, are x minus c. So it definitely looks a little bit different. But it's the same idea. It's the y values on top, the x values on the bottom. We're just naming them differently. But now I still want this gap to disappear, but I don't have an h or anything like that. Instead, what I'm going to say is I want x to approach C. I want that second point to get close to the first. So both of these are totally fine. They both mean exactly the same thing. They're both going to find the same thing. It's just sometimes one is easier to use than the other. But this is now how we're going to actually be able to calculate the slopes of a tangent line. We're finding the slope of a secant line, but we're bringing that second point in until it basically becomes 1 point. Now, check out what happens with both of these if we just plug in the value, right? Like, think about this. The limit as x goes to c. If we were to plug in c, we would get f of c minus f of c over c minus c. Well, that's 0 over 0, which we've seen as an indeterminate form. It could be anything. And we had to play some sort of an algebraic trick. If you look at the other one, as h goes to 0, f of c plus h is f of c minus f of c over 0. So again, another 0 over 0, which means do algebra. So no matter what, for any one of these kind of problems where we're finding an instantaneous rate of change, we're going to have to do algebra. The only question is, what kind of algebra? All right, so let me leave you with an example. We'll wrap up today with an example here of actually calculating the instantaneous rate of change, slope of the tangent line, using both these methods. We'll do it once with each one of them so you can see you get the same thing. And we'll go back to our good friend x squared. And let's do this. Let's find the instantaneous rate of change at x equals 1. And I'm pretty sure we've done this one. I think this was one of the first examples I did with you guys, and we tried to make a good guess of it. If you go back and you look at your notes or you go watch the videos, pretty sure we found something that was near 2, right? I think when we started plugging numbers, we got like 2.1, 2.01, 2.001, and it definitely looked like it was going towards 2. Well, now we'll see how the calculus shows that it must equal 2. All right, so we're going to do it both ways, but let me just first help you kind of see what's going on with all the different letters and all that. So in this case, f of x is x squared, but c is equal to 1, because that's the point at which we're interested in. What's going on as we're near 1. Okay, so I'm going to use both of these so you can see that they both work. So let me start with this bottom one. So to get this instantaneous rate of change, so we'll call it m, it's going to equal the limit as x approaches 1 of f of x minus f of 1 over x minus 1. Okay, so I just replaced the c with 1. Now let's evaluate that top. Let's put in x and 1 into the function. So f of x is x squared. When I plug in 1, 1 squared is 1. So we get the limit as x goes to 1 of x squared minus 1 over x minus 1. Now, don't bother trying to plug it in, because no matter what, at this point, when you plug it in, you're going to get 0 over 0. So let's immediately jump to doing algebra. In this case, it's going to be factoring, right? We've got x squared minus 1. That can factor as a difference of squares. We get x minus 1 times x plus 1. The x minus 1's cancel. So we're left with the limit as x goes to 1 of x plus 1, which is 2. So we know the slope of the tangent line is 2. We know the instantaneous rate of change of this function is 2. 2 whatevers, 2 meters per second, 2 miles per hour, 2 whatevers, right? But that is the slope of the tangent line. All right, so that's what this form got us, is 2. Now I'm going to show you that the other form also gets us 2, because I want you to see that they both work. And what you're going to see later is that which form we use kind of depends on what we're starting with and what we want to do. So it's just good to have more than one form. Well, let me start writing out this one. So this one, we're going to have the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. So again, everywhere there was a c, I just put 1. All right, so let's plug those into the function and see what this does for us. So we're going to get the limit as h goes to 0 of 1 plus h squared minus 1 over h. Again, don't bother trying to plug in 0 because we know it will fail. So instead, let's do algebra. So I'm going to multiply that stuff out on top. We can get 1 plus 2h plus h squared minus 1. 1 minus 1, those are going to cancel each other off. So I'm left with the limit as h goes to 0 of 2h plus h squared over h. Now, this one I'm going to factor. Because I can pull an h out on top. Now my h's cancel. So the limit is h goes to 0 of 2 plus h, which is 2. So both of them got us to the same place. Both of them gave us the same slope, which is good, because they should. It's just two different ways of thinking about it. This first one is saying, bring the points together. The second one is saying, make the gap between the points go away. It means the same thing, right? And the end result is the same. It's just two different ways of looking at it. But either way, we get to the slope of the tangent line or the instantaneous rate of change. Well, believe it or not, you just did calculus. You just did calculus. It's what we call a derivative. We'll talk more about this on Wednesday. But this is why we talk about limits before we can actually dive into calculus, because calculus is all about limits. All right, so this is where I'm going to end it for today, but just so you know what's coming up. First of all, on Wednesday, what we're going to do, we'll go over the quiz, because everyone should be done with it and I'll have it graded. So we'll go over the quiz, answer any kind of homework questions, all that good stuff. But then we're going to keep going with this. We're going to keep looking at this derivative idea, and we'll talk about what it does and how it works and all that. Okay, so that's what we're going to do. But then also don't forget homeworks. The next set of homeworks are due tonight at midnight, so make sure you get in there and work on the ones that are due tonight. Anyway, so let me go ahead and end the recording then, and I will chat with you guys later.